This talk is about Modia, an experimental language with many similarities to Modelica. The work has been a collaboration between Martin Otter, Andrea Neumayr and Gerhard Hippmann at DLR and myself. Last year we started a completely new design of Modia. The essential of this presentation is I will talk about simplifications and unification of constructs. Andrea will talk about the coupling between Modia equation-based modeling and Modia 3D, so multibody. We have had a focus on scalability, and Martin will talk about that, and also about the use of differential equations.jl. I will first explain the basic language elements of Modia. A connector to be used in an electrical circuit is defined in this way. It's a model with two variables, V and I, which are potential and flow. This is used in a one port to define P and N connectors. And one port also contains some equations defined in this way. The one port can be inherited by a resistor. This is expressed by a merge operator between one port and another model consisting of a resistance parameter with a missing value so far and one equation for Ohm's law. Such a resistor can then be instantiated in a circuit model, and at that time also merged with another structure, a map, defining what is a resistance value. Note that units can be utilized in that way. There are three essential language elements in Modia: model, var, and map. These are all of them hierarchical dictionaries. So a model is a dictionary of variables and components and an array of equations. Var is a dictionary of variable attributes, min, max, etc., and also domain-specific attributes that are user-defined. Map is also a hierarchical dictionary to set and modify parameters. All these dictionaries are then combined with a merge operator. That is a hierarchical merge, and that is used for inheritance. So merge between models, including concatenation of the equation arrays. And also for setting parameters, numeric and also generic parameters that we will talk about later, and modifying parameters. The merge function is actually very simple, and a simplified version is shown to the right. And of course it's a recursive function, and by the way there is a typo in the paper that is corrected here. I will now explain how the resistance R of the circuit is defined. We start with the one port and the pin and the built-in flow and potential definitions. The pin is substituted, and also potential and flow are substituted, which means that an expanded version of one port 3 looks like this. This is then merged with another model consisting of just the parameter R and one equation. And these are added, and we have the resistor definition in this way. In the circuit, it's then added the parameter set with a map, which overrides the missing value of R, and we have a specific value in this way. We have recently introduced another syntax, a little bit more high level and more Modelica-like, using Julia macros. So instead of using this map definition and a merge operator, it's possible to use a usual constructor syntax. It's also possible to use nested modifiers in this way. All this is translated to merge and map in the following fashion. It's possible to use dot notation as well, and again, it's translated to map and merge. Using Julia macros allowed us to introduce generics in the sense of the concept of replaceable model and replaceable component in Modelica. And these are then the corresponding syntax in Modia. This enables us then to, for example, define a circuit, to modify this circuit by defining a new device type capacitor with a default value C equals to 2, and also to change the source to be a constant current instead. More elaborate cases are shown here as well, where the device type is changed to capacitor, but device 1 is changed back to become a resistor.
I am Andrea Neumayr, and I'll show you how to deal with domain-specific algorithms based on 3D mechanics. In this short video clip, you can see two cooker robots playing around with a solid ball. 3D mechanics is about physical behavior. This means each robot has mass properties, and also about collision handling, because the grippers are colliding with the ball. An object 3D is the core element of Modia 3D. It is located relatively to its parent. If it should have physical behavior, it's defined as a solid feature. The world object 3D is the only one with a scene feature. A robot consists of several links, and each link is composed of 3 object 3Ds. The first one defines a solid geometry, and the 2 others are for connecting those links. Each link is driven by a motor, and the motor is connected to the link via a gear and steered by a controller. The here presented models are automatically converted from Modelica to Modia. Let's build up a U-bot model. It consists of the 3D mechanics, where we already introduced 2 links, and those that are connected via a revolute joint. It is driven by a motor, and the equations are connected via its flanges. At least we need to instantiate the model. But beforehand, the domain-specific function build Modia 3D needs to be called. So let's have a look behind the scenes. An interface between Modia and Modia 3D is done with the help of Modia parameters. We use a predefined key where we insert a Modia 3D struct name. Further key-value pairs are possible, like you can see in the example on the left-hand side. There are 2 steps. One where we create a parameter dictionary, and in the second, those parameters are evaluated. Therefore, we get a direct reference to an object 3D struct. So let's define some domain-specific equations for the revolute joint. First, we need some parameters, a 1D drivetrain, and at least some variables with initial conditions. The relations between the variables are given by equations. Let's have a look at our domain-specific function, build Modia 3D. It traverses through Model 3D and collects all the information about 3D mechanics, and it is merged with the following 3 equations. The first one returns a reference to the scene, where all the information about 3D mechanics is stored. The second one stores the actual values of joint states in joint objects. And the third one is a domain-specific algorithm. It computes the joint forces from joint acceleration. So these 3 equations are independent of the size of the 3D system, and the generated Julia code is really compact. These 3 equations are sorted with all other Modia equations, and a linear equation system is solved numerically at runtime. The here presented technique is a generic one, so you can use it to combine your own Julia models with the equation-based concept of Modia.
Hello, I'm Martin Otter, and I will give you some information about one of our benchmarks. The benchmark is a mobile, so a tree-structured system built up of 3D mechanics elements and of Modia equation-based elements. We have a tree depth of 1 to 10. If depth is 10, you have about 3,000 states and 500,000 of scalar unknowns, and about 7 of an equivalent Modelica model, and about 7,000 components. When you call build Modia 3D, you can define in which way the code is generated for the 3D mechanics part. Time to start simulation means to read the model, perform symbolic transformations, generate and compile the code, and start the code. We compared Modia with two methods with two commercial Modelica tools. Here we just show the better of the numbers from the Modelica tools and Open Modelica. As you see here, roughly Modia start time is about 1 to 2 orders of magnitude faster as with these Modelica tools. The reason is simply because the Modia code contains just 3 function calls for the 3D mechanics part, whereas the Modelica tools have to go with a huge number of 3D mechanics equations that are present in the code. The simulation time is roughly the same for Modia and for the Modelica tools if a ODE solver is used, here Sandial's CVOD. However, if a DRE solver is used, here Sandial's IDA, then Modia is about a factor of 100 or 200 faster as when simulating with an ODE solver. The reason for this is that in the model there's a large linear equation system, and Modia has a new technique that whenever a DRE solver is used, then linear equation systems in the model are solved from the DRE solver if they have a certain size and not in every model evaluation. And this gives a huge speed up in these cases. So Modelica tools could use the same technique and could also get a speed up of 100. You have several operations that you can perform in Modia models. Of course, you can simulate, so you provide an integrator from differential equations. You may optionally change parameters with a merge command and plot. So the standard. Then you have a very powerful feature that this merge command can also read a radical map from a JSON file. So the data, the parameters, including units, are stored in a file, and you just merge them into the model. A merge command can also contain uncertainties. And then for the instantiation, you have to define a floating type of measurement. And then linear error propagation is used to propagate these uncertain values to all variables and to the simulate and into all time instance. As a result, you get something of this kind. You get the nominal value of this curve and then the uncertainty range with linear error propagation theory. In the same way, you can also perform Monte-Carlo simulations. You can provide various distributions for your uncertain parameters, and then as floating point time, you define static particles from the Monte-Carlo measurements package. You define here 100 particles, which means 100 simulations. As a result, you get something of this kind, where you have the mean value and all 100 simulations of the Monte-Carlo simulation. You can also simulate until a certain stop time and then analytically or numerically linearize and get the linearized system back and the linearization point. And if a floating point type of measurement is used, uncertain values, then the linear matrix has also uncertain values.
We have introduced a new design of Modia, which is simple but yet very powerful. And in particular, we have shown how equation-based modeling can be combined with domain-specific modeling by using Julia functions. This has been done for multibody systems. This enabled us to get very fast translation and orders of magnitude faster simulation. So all this is very promising, and you can look for more information at the GitHub pages for Modia sim/Modia. And furthermore, we want to start a dialogue with potential users, and for that we are planning a web meeting in end of October to discuss plans, priorities, and collaborations. So please send me and Martin Otter an email if you want to participate. Thank you very much.